Today I want to talk about some summations, okay? And before we start summations, I'm going to define a few things, right? And I want you to notice, although I'm going to provide all these definitions for the properties, it's not my intention to actually prove any of them, but I'll talk about that later. But for now, summations. First, we're going to define what a final segment of the natural numbers is. So we say k is a final segment of the natural numbers if and only if for some n not in the natural numbers, k is just the set of all x in of all natural x such that x is greater than or equal to x naught. Hopefully, if this doesn't make sense, some examples will clear this up, but you do need to know this for sequences. So the natural numbers is a final segment of the natural numbers, right? N naught is just zero. Um, right? N naught is just equal to zero. In other words, the natural numbers, right, is a final segment because it is just the set of all x in the natural numbers is that x is greater than or equal to zero. But that is just the natural numbers, right? Also k1, which is 3, comma 4, comma 5, comma 6, comma 7, comma dot dot dot, is a final segment, right? And not is 3. It's of the form all the numbers starting at some point onwards, right, with no gaps in between. On the other hand, 101, comma 102, comma 104, comma 105, comma dot 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 is not a final segment because 103 is excluded and thus it is not of the form x is greater than or equal to some x naught, right? Because you're not including 103, which is greater than or equal to whatever, what greater than or equal to 101. So now that we understand what a final segment of the natural numbers is, we're going to use this in defining a sequence. And a sequence is actually simple. It's a function whose domain is a final segment of the natural numbers and whose range is a subset of the reals. So its codomain is the reals, okay? And our function is going to be a, right? So this is just a final segment of the natural numbers, and this is to the reals. And a of n, right, which is a function notation, is just commonly written as a sub n, okay? This is a notational choice. So here's an example of a sequence. A of n, which is just a sub n, we're going to say it's cosine of n, right? In this case, our domain is the natural numbers, right? And indeed, we showed that it is a final segment of the natural numbers, so that can be our domain. And I chose cosine of n because it's important to illustrate that its domain has to be only natural numbers, right? Or final segment, more importantly, right? So, for example, if we know that it's defined for 0, it has to be defined for any number greater than 0. That's another key property. So a sub 0 is cosine of 0, a sub 1 is cosine of 1, a sub 2 is cosine of 2. And even though these right here are not necessarily natural numbers, we don't care. They are real numbers, right? They are real numbers. That's the important part. And the domain is natural numbers. And here's another example illustrating a notation, right? A sub n, which is 1 over 2 to the n. A sub 0 is 1, a sub 1 is 1 half, and a sub 2 is 1/4. Now, a recursive sequence is a sequence where the first term or terms are given, and each subsequent term is defined based on the previous terms. An example is the Fibonacci sequence. Okay, it just says um, any term is the sum of the previous two terms, right? And the first two terms, a sub 0 and a sub 1, is just 1. So it starts at 1, comma 1, then the sum of those two is 2, the sum of these two is 3, the sum of these two is 8, and so on and so forth. Now we kind of want to talk about sums. So sums, we want to quickly notate large or infinite sums, right? So what we're going to note is a sub 1 plus a sub 2 plus dot 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 plus a sub n is just equal to the following sum, okay? So we have a sigma, we have an index of summation, typically k, I, or j, right? We have a lower limit of summation, that's our original input, and then an upper limit of summation, which is up to here, right? So this is what this sum is, right? The lower limit of summation, by the way, doesn't have to be 1, it's just in this case. And what we're summing has to be a sequence, guys. That's very important. As well, since it is a sequence, m, which is our lower limit of summation, right, as I showed here, it's just m. In this case, m is equal to 1, but that has to be greater than or equal to 0 because a sub k is a sequence, right? It can't be negative. And the lower limit has to be less than or equal to the upper limit. All right, and this is our intuition for what a sum is. But we can more precisely define it because this is kind of loose. So a definition of a sum, okay, we're going to use a recursive definition. So we're going to define a sum from k equals m to n of a sub k as just a sub n, right? That's the, first term. And then recursively, we know we're going to define the sum from k equals m to n plus 1 of a sub k as the sum from k equals m to n of a sub k plus a sub n plus 1. Right. And this is consistent with our intuition for summation. You can take some time to verify that indeed you're just going down all the way from n plus 1 to n minus 1 to n minus 2, all the way down to m, and you'll end up getting this as I noted it right here. So there are some properties. Like I said, all of these properties, all of these sums, I will not prove it, okay? There are as many proofs that exist. You can search them up. They're interesting. I agree, but my purpose here is not to prove them. It is moreover, it's more to prepare for Riemann integration, right? If that makes sense. So linearity, okay? Hopefully you should know what linear combination is, but linearity applies as follows. So you can factor out a constant and split a sum. Crucially, this constant, right, it doesn't have to be a constant in the sense that it has to be 2, 3, 1/2. It just has to be constant relative to the variable which is in the index of summation, right? It just has to be constant relative to the index of summation. So even it could be n, for example. We could factor out an n, and even though you see an n here, right, that's a fixed number relative to the index of summation. As well, the upper limit of summation has to be constant relative to the index of summation, right? This n has to be constant relative to k. It can't vary. That's another thing. Associativity, right? If you're adding all the numbers from L to N of a sub k, right? We could just split that from L to N and then from N plus 1 to N, right? Of course, M has to be less than N. Now, this is more important though, as we can rewrite this as, and I just realized I wrote this wrong, but it's okay. We can rewrite this as a sub, by subtracting, we can get that the sum from k equals n plus 1 to n of a sub k is the sum from k equals L to n of a sub k minus the sum from k equals L to m of a sub k. So if we ever want to express it with a new lower limit, of course, we can just take it from L to n and then subtract what we added. And hopefully that'll make sense through examples. Translational invariance, okay? If you add something to the upper and lower limits of summation, and you subtract it from the index, right, wherever you see it in the sequence, you're going to get the same exact sum. And that intuitively should make sense. And finally, telescoping, another interesting property. It just states that this sum right here, which is of the telescopic form, the reason why they call it telescoping is because telescoping in math basically means when you express it all out, a bunch of things just cancel out and you're left with a much simpler result. In the same way, when you express the sum, all of these middle terms cancel out and you're just left with a sub n minus a sub n plus 1. If you want to memorize it, you want to take the smallest one, plug in the lower limit, and take the larger one, plug in the upper limit. Okay, and this is what you get. Little Gauss. It has an interesting history. I won't explain, but it's called Little Gauss, obviously after Gauss and his discovery when he was little. Like I said, I'm not going to talk about the history, but I would personally recommend that you look it up because it's honestly really interesting. But it just says that the sum of the first k positive integers is, n positive integers is n times n plus 1 over 2, right? Pretty simple to memorize, I think. And you may have learned this before, maybe in pre-calculus, I don't know. Now, we also have geometric series, okay? This one's a bit harder to cram, but hopefully you can do it. So for x is a common ratio that's not 1, right? The sum from k equals m to n of x to the power of k, crucially the index of summation is in the power, right? Is just x to the power of n minus x to the power of n plus 1. over 1 minus x. I don't think it's too difficult, but I think that one might be the hardest one to memorize. Now, special sums. Now we have the sum of a constant. We could just see the constant times n, right? Because we're adding c n times. K squared is n times n plus 1 times 2n plus 1 all over 6. Or maybe you might see it like n cubed over 3 plus n squared over 2 plus n over 6. Actually, believe it or not, Mathologer has an interesting video that I'll try to link, hopefully if I remember, explaining, and it uses this notation, by the way, and there's a pretty important reason why. But he explains a bit more about all of these sums, right, and how to derive them. He explains, if I remember correctly, why we have this and its relation, this discrete sum and its relation to this continuous sum, and the fundamental theorem of calculus, and why this takes the form of an antiderivative, right? And then obviously you have some error terms, but that's there. So I would highly recommend that video. Does have proofs. It talks about all sorts of interesting stuff. Here, the sum of the cubes, right? Whenever you have cubes, it's just the same as, believe it or not, remember, little Gauss squared. So n squared times n plus 1 squared all over 4. Like I said, there are numerous proofs of all the facts I provided, but it's not my intention to prove them here. Practice. So I have some practice problems. I have quite a few that hopefully cover the full scope of everything that I've shown here. This first problem, I'm looking at it and I'm thinking, I don't know anything about sine, and why do I have k squared here? So what I'm going to focus in on is the fact that I have k plus 1 and k, right? This should ring a bell. Oh, maybe this thing telescopes, right? So our sequence, you don't have to write this, but our sequence is going to be sine of k squared, right? And this thing doesn't actually telescope immediately, remember? So we're going to rewrite it, factoring out a minus this time, right? K equals 3 to 1,000. We can do this by linearity. And now maybe it becomes a bit more obvious that, oh yeah, this thing does indeed telescope, right? So this becomes negative. What? Okay, well, telescoping, right? We take the lower one, we plug it in, so sine of 3 squared, and then, of course, minus sine of, we take the upper one, so 1001 squared, right? So this is a telescoping sum. Don't get lost with the sign, just focus on telescoping, okay? This one. Now we have a formula for I squared, but it has to start at 1, right? So how are we going to do that? We're going to do associativity. We want an index of 1, right? But in order to do that, we need to subtract out all the terms we added, which is from 1 to 4, right? Because 4 is not included, but 5 is. So this is, of course, 101. No, sorry. This is going to be 101 times 102 times 101 times 2 plus 1, or you could write it the other form, I don't really care. 6 minus 4 times 5 times 4 times 2 plus 1 over 6. And I won't simplify that. You could do that. So, next one. Here we're going to use linearity, okay? I equals 1 to 100, 4 plus sum from I equals 1 to 100, 3i. Okay, and remember, this is the 4 times 100 plus 3 times 100 little Gauss times 101 over 2. Okay, moving on. Here we have a form. We don't have a formula, so we could expand, sure, but I think it's easier to use translational invariance because we have an I minus 5 here, right? So that should tell us, well, we have a formula for I squared. So what if we make this I squared and adjust the upper and lower limits of summation? So in order to do that, we want to add 5 to the index here. So we're going to subtract 5 from the upper and lower limits. So that'll look like 1, 5, I squared. Oh, okay, but this is significantly easier to do, isn't it? We already have a formula for that, and I'll leave that as an exercise to you. Okay, very simple. Now the next one, you see natural logarithm why would you panic? You would think, natural log, I don't know how to do this, I'm skipping it. Don't panic. Notice I plus 3 is 1 greater than I plus 2. So this is a telescoping sum, right? So obviously we don't care about the natural log part, we care about the telescoping part. So similarly, this is the larger one. So this is this second term and this is the first term, or you could say something like that, right? Right, first term, next term. So we're going to take the first term. So we're going to take the larger term. We're going to plug in our value of n, which is minus, plug in the lower limit, and this is the natural log of 8 minus the natural log of 3. And it should be relatively easy to solve, right? Hopefully this is an easy way to remember telescoping. And by the way, you don't have to simplify this. I mean, I just left it. And here we get to the harder sums though. Now, the reason why these problems exist are because the problems I gave with summations are great, right? We love them, blah, blah, blah. But this is where we really need summation, right? The final problem especially, which is basically a Riemann integral, okay? So this problem, how are we going to do it? Well, I want you to remember this pattern. This fraction right here maybe looks like it telescopes, but we don't know that it does. So what we're going to do is we're going to first evaluate that sum, right? And how we're going to do it, we're going to use, if you want to search up the term, partial fraction decomposition. That is to say, we decompose this fraction into a sum or difference of partial fractions. In this case, if you remember, maybe you learned from algebra, from pre-calculus, how to do partial fractions. You need to know this, by the way, for indefinite integration, but that's for another topic. Of course, you could just check your work, right? Express it like this with the minus. Check your work by cross multiplying. You'll get this. If you need to, just search up partial fraction decomposition, and you should learn how to do that, right? But this is easy. This is telescoping, okay? So this is just telescoping because we have the I and the I plus 1. So this is going to be the limit of 1 over 1 minus 1 over n plus 1, which is the limit as n approaches infinity of 1 minus 1 over n plus 1. Okay, but this is going to approach 0, so we're just going to get 1. Okay, that wasn't too hard, was it? And if you want though, this next problem here especially is going to be quite long, but bear with me, okay? So this one hopefully is the one that if you can get this down, you've mastered all your formulas. And I didn't include a geometric series problem, so do remember to practice geometric series. I didn't include it, right? Okay, so in order to do this, first notice 1 over n and 3 are both constant in respect to the index of summation. We're going to take this out, express this sum here, n of 1 plus I over n squared. And before we do that, we're going to evaluate that sum, right? Because we obviously want to evaluate this sum. So how are we going to do that? Well, first, unfortunately, we can't do any smart properties. We're just going to expand it. 1 plus 2i over n plus I squared over n squared, right? Okay, and what is this sum? Well, we're going to use linearity, and we're going to get the sum from I equals 1 to n of 1 plus the sum from I equals 1 to n of 2i, or sorry, not even, remember we're using linearity. 2 over n is constant in respect to the index of summation, and then plus 1 over n squared again is constant. And I'm not going to write the upper and lower limits, but it's implicit. And that is equal to n plus 2 over n times, hopefully you know your formulas here, over 2, plus 1 over n squared times, what is the formula? And of course, check that the index, that you can use it, but of I squared, well, remember that's n cubed over 3 plus n squared over 2. And easy to remember it is that you add 1 divided by the exponent plus n squared over 2 plus n over 3 times 2, which is 6. Okay, so this is n plus, these cancel out, n plus 1 plus n over 3 plus 1 over 2 plus 1 over n over 6, right? And this is just equal to, what, 2n plus 3 halves plus n over 3 plus n over 6, I guess. And I'll leave it like that for you. Okay, and now we're going to plug that back into our limit. So I'm not going to rewrite this, but do note I'm continuing from this step onwards. This implies that that whole thing at the beginning is equal to the limit of this one, 3 over n, times 2n plus 3 over 2 plus n over 3 plus n over 6, right? And this is the limit as n approaches positive infinity of, we're going to expand it out now, we're going to get 6 plus 9 over 2n plus, so those n's cancel out, and that becomes 1, and that becomes 1 half, right? And of course, this term is going to go to 0 because it has an n in the denominator, hopefully no rational functions, right? And all in all, you're going to be left with 6 plus 1 half, right? And, is that right? Plus 1 half. No, there was, I'm going to check again, but, okay. Yeah, okay, I got it. 1 over 6n, right? Yeah, okay. Sorry, so when I was doing this, this should have canceled out and it should have been 1 over 6n. So this is 1 over 6n. So this is 1 over 6n. Sorry. Yeah, that's definitely my bad. And you're gonna get something here that'll become like, well, 1 over 2n squared. So in reality, you'll only be left with, this goes to 0, this goes to 0, so you'll just be left with 6 plus 1, right? Hopefully that's clear, which is equal to 7. Okay, so this limit, all in all, turns out to be 7, right? So hopefully you got this because we're going to be using in the Riemann integral. And again, I'm sorry about the tiny mistake. It happens. Be sure to check yourself on that. So yeah, and hopefully the summation video helped. If there's any specific thing you need, feel free to reach out to me and I can try to explain as best as possible. And yeah, actually, you know what? Good luck in your studies.